Okay, so here's why we want to be able to use those summation formulas and what we're going to be focused on for the rest of the year, and that is finding areas under curves. That's what calculus has a very usefulness for. And so I could approximate the area under the curve or between the curve and this x-axis. So I'm interested in how much is this area? Well, of course, I don't have a formula like I have nice formulas for rectangles and triangles and all that good stuff. But I could section it off into some rectangles. And so I'm looking at the area between the curve and the x-axis. Later, of course, we'll mess around with that. And n is going to be the number of rectangles that I can make in that space. And we might refer to them as subintervals. That's the fancy way of talking about them. And if my function, so here's f of x, my curve, so if f of x is increasing like it is, then the right endpoints, let's fix this here. So if f of x is increasing, then I'll use the right endpoints and they'll give me an upper sum. You'll see here in a minute when I draw it in. And if it's increasing and I use the left endpoints, so this is true for both, I'll get the lower sum. And again, you'll see what I mean when I draw these in. So very important first that you make sure that each of these distances between your subintervals is exactly the same amount. So this spacing is very important. And since it's on the x-axis, we're going to call this delta x. So I want to make sure that delta x is the same amount every single time. So as you draw those, pay attention to detail and that those widths are exactly the same. And then what's happening along here, we can label each one of these as x sub 1, and this is the second x value, and this is the third x value, and the fourth x value, and the fifth x value, and the sixth x value. So now I want to finish these rectangles. And they have a fancy geometric name. They're called circumscribed because they actually end up falling outside. Circumscribed rectangles. And so if I find the area under or within these rectangles, I know the area answer is going to be over because, of course, I have this extra space that's a little too much, and a little too much, and a little too much, and so forth for all 6 of these rectangles. And oh, one more piece that I want to add on your diagram is we are looking at the area in the interval A to B. So the area under the curve between A and B. Okay, so now I want to label these y values. So of course this is f of x sub 1, and this one is f of x sub 2, and so forth, all the way up. Takes a long time to draw all of these, doesn't it? All the way up of course, to f of x sub 6. So those are all the corresponding y values. So now, if I want to find the area for this, I would actually recommend that you write this down below here, but since I didn't leave enough space and I can't scroll up with this program, I'm going to write it up here in this upper piece. I won't make that same mistake twice on the next one. So now, here's what I notice. So every single one of those rectangles, I have to do width times height. So for this first one, we'll call them number 1, I would do delta x times f of x sub 1. And then for the second rectangle, the width again is delta x, and the height is that y value, which is f of x sub 2. And I would continue that pattern for rectangles 3, 4, 5, and 6. And so, okay, of course, for rectangle 6, the width of the rectangle is delta x, and then the height is f of x sub 6. And so I notice, hey, there's a pattern here. So I'm adding up, and I like to use I. And so I notice what's different about each one. Well, the only thing that seems to be different is this number, the little subscript. And so I could put the delta x either in front, or I could put it after the sigma, my choice. So I could put delta x here. And then the terms that are changing are the f sub x's. And what I notice is that I start at 1 and I go until I hit 6. And of course this is my area, right? Because that's what we said we were trying to do, is find the area of all the rectangles. And so again, you need to make sure that all these rectangles are the same width. Again, we're going to call it delta x. And likewise, we're going to label each of the x values. So now here's what we're doing this time. This time we're actually inscribing the rectangles. Remember last time they were circumscribed. This time we're going to inscribe, which means when I draw them in, because I want to use the left endpoints, it's going to look like this. So the left endpoint is the one I make the height. And so inscribed rectangles. And so now this time my area will be under, because I'll be leaving out this, and oops, I didn't include this and this. So the area under that curve, I'm going to basically underestimate by using the left rectangles. And additionally, when I label these, I'm going to call this x sub 0, x sub 1, x sub 2, and 3, and 4, and 5, and 6. And if you note, if I number these, I have 1, 2, 3, 4, 5, 6 rectangles still. And so now, again, I'd like to label their y values. So this one would be f of x sub 0. Oops, struggling here. So f of x sub 0, because it's the height right here, and then this one is f of x sub 1, and this one is f of x sub 2, and so I'm going all the way up to f of x sub 5, because the height of this rectangle is the y value for x sub 5. So now when I write out the area formula for this, so for the first rectangle I'd be doing delta x times f of x sub 0, and for the second rectangle, rectangle number 2, the width is delta x, the height is f of x sub 1. For rectangle 3, the width is delta x, the height is f of x sub 2, and all the way up to rectangle 6, whose width is delta x, and the height is f of x sub 5. So this time I notice, again, what's changing? Oh, it's really just this bottom number. Everything else seems to stay the same. So I'm summing up, and remember, since they all have this, that I could just put that out in front. Again, I can put it in front or put it afterwards. It doesn't matter. As a matter of fact, I'll write it both ways. And then what I notice, I'm going to let it be I again, and I'll start at I equals 1. Is that I'm doing f of, oh, actually, I don't want it to start at 1. I'd like it to start at 0, right? And then I can call it I. And same thing here. And I notice that it goes all the way to 5. So where the circumscribed rectangles went from 1 to 6, the left endpoints, or the inscribed rectangles, go from 0 to 5. And remember, this one is going to give me an answer that's a little too low. The other one's going to give me an answer that's a little bit too big. Now, one more thing I'd like to add. If I were to do this generically, let's say I didn't know how many rectangles I needed to go out. So on this one, I would still have that delta x, because they'd all be the same width, whatever that was, and I'd be going to f of x sub I. But if I start at 0, notice that I'd be ending one less than whatever this was. So notice I didn't go all the way to x sub 6 because I'm doing a left endpoint. So I'd be going to n minus 1. Versus over here, if I did it generically, I would have been going from I equals 1 to n, because I did go all the way to here because I was using the right endpoint. So this would have been, I would have gone all the way to n as opposed to n minus 1. So those left endpoints, I started at 0 and went to n minus 1, versus the right endpoints, I started at 1 and went all the way to n. So that's the difference in the two rectangles. And keep in mind, one of them overestimated and the other one underestimated.